Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. Now, where we're going to go to give you kind of a roadmap for several lectures into the future, parallax is important because it's our first step in measuring distances farther and farther in the universe. I'll give you the rest of the measurement techniques so that when they start coming up, you say, oh, okay, this was, that parallax lecture. So after we get parallax, we can actually find a new pattern, which is called the main sequence fitting. We'll have to go in and talk about the birth, life, and death of stars along with that process. So we'll find ourselves jumping back and forth between measuring distances and talking about stars and the nature of stars. After that, once we get the main sequence fitting technique down, that pattern will actually recognize a second pattern called period luminosity. And so that pattern isn't possible to observe until we have the main sequence pattern down. And then lastly, supernova. And there's actually one that goes past this, that I left it off the list, called Hubble's law. Now, collectively, these 5 techniques, plus a couple others, are generally referred to as the distance ladder. That name is given because you can't arrive at a pattern higher on the distance ladder without observing the previous pattern. So, parallax. Let me give you a demonstration first of all. Okay, sit here, stand back just a little bit, hold your thumb out at arm's length, okay, and close one eye. Okay? Hold your thumb out at arm's length, close one eye, and go ahead. Center your thumb on that light green in the middle of the screen. Okay? Now, without moving your thumb, without moving your arm, go ahead and just swap eyes. Okay? Just open up a different eye. Okay? Go back and forth. And what do you notice about your thumb? Yeah, you should have noticed that it shifts. And the question I have for you is, why does your thumb appear to shift? Yeah, good. Your thumb appears to shift because you're viewing it at a slightly different angle. Right? When I did this, I'm actually viewing my thumb with my left eye. And so I've lined my left eye up with that center green strip. So when now I switch to my right eye, because my left eye was lined up, when I switch to my right eye, it's viewing it at a slightly different angle. And so I see my thumb appear to jump, appear to move to a different position with respect to the background. Okay. That is the parallax effect. Now, how do we take advantage of that? Our brain uses this parallax effect to take the slightly different viewing angles from each individual eye, the right eye and the left eye, and your brain takes those two separate images, overlaps them, and gives you the 3D perspective. Of course, in the old days, you could also do one image. Instead of having to force your eyes to overlap the images, defocus, if you will, you can present it as one image and use the colors to control which image goes to which eye. Yeah, okay. So let's go ahead and I got another question for you here. So let's go ahead and I call this painter's thumb. So go ahead and do painter's thumb, but I have a really important question for you. As your thumb moves closer to your face, what happens to the shift? Yeah, you got it? Yeah, good. So we start off, if your arm is fully extended, you notice you can measure the shift. Mine goes from the center green to the yellow. But as let's say I bend my arm only halfway and I do the same thing, you notice now that your thumb should jump a larger distance, right? As the thumb gets closer to your face, the viewing angle gets more extreme, and so you should notice that your thumb jumps a larger distance. We could go the opposite way as well. As you move your thumb further away, the viewing angle gets less extreme, and so you shouldn't see the object jump as much. So that's qualitative. Let's go ahead and quantify it. So first of all, the formal definition, it's the parallax is the apparent shift of nearby objects due to different observing locations. So now you might ask, how do astronomers use parallax? And it's not like we set up two telescopes, just, like telescope A is over here and telescope B is over there, and we look at the object at two different viewing angles, okay? The problem is that the Earth is just too small to measure parallax in that method. So how we use this, okay? Imagine for a second you are on the Earth with your nice little telescope, say you're looking right here, and what you're trying to do is view this distant star. Because you are looking at this distant star. This is the line of sight to that star. And at this location, you see the star in the green section of the sky. Now, of course, usually we don't color the sky different colors. It's background stars that we're comparing to, but this is illustrative purposes. So now, what next we do? We wait 6 months. We go ahead and we wait until the Earth has moved to the opposite side of the sun. And again, we do that measurement of that nearby star. We go line of sight, and now we'll see that star against the yellow part of the background sky. Okay. So rather than using two eyes, if you will, at different locations, we're using one telescope and we're standing here. We're waiting 6 months, and we get to here and view it again. And closer stars will appear to shift due to that background. Okay, now you actually know how much the star will appear to shift if I give you the distance. Okay? For example, if I tell you that this distance is, let's see, 1 parsec, so 3.2 light years. If this distance is 3.2 light years, how much is that object going to shift? Just take a guess. Yeah, 3.2 light years, or I guess I could tell you this is 1 parsec. Yeah, that parallax angle is going to be 1 arc second. Okay? So that's really where we get that unit of parsec from, is that we're thinking of this parallax, right? Parallax of 1 arc second. When we have a parallax of 1 arc second, the distance is 1 parsec away. So quantitatively for you, I've got an equation here, and they're inversely related. Okay. So the apparent shift of the object in arc seconds is inversely proportional to the distance to the object in parsecs. Okay. So this is how we quantify it. And notice this is a non-SI unit. So I'll put that down here, non-SI units. So here's the question. The next closest star to our sun is Alpha Centauri. Okay. And I've actually given you the distance in parsecs, 1.3 parsecs. That corresponds roughly to about 4 light years. Okay. And based on the parallax measurement, okay, why did Greek astronomers think that all stars were the same distance away? Okay. So the first thing I recommend you doing, go ahead, find the parallax angle. Okay. And then I need you to sit down and think about why ancient Greek astronomers would think that all stars are the same distance away. Go ahead, take a minute. You got it? Yeah, good, 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 good. So let's go ahead. Let's first of all find the parallax angle. Okay. And yeah, so the fortunate thing is I've already given you the distance in parsecs. If I had given it to you in light years, you would need to convert it over into parsecs first before plugging it into this equation. Okay? So that's the first thing. The distance has to be in parsecs in order for this equation to work properly. Okay. So I go ahead and I plug it in, and 1.3, that's 4/3, so 3/4. So we're going to get something about 0.75. Okay. You can think of, yeah. Okay, and so we go ahead. We get 0.77 when we actually plug it into our calculator. So why did ancient Greek astronomers think that all stars are the same distance away? They had an idea about this parallax method. They even had an idea about stars shifting in space. Yeah, good. They didn't have the ability to measure such a small angle. So they go out, they measure the parallax of the stars and find that none of the stars shift with respect to background stars. Well, that means that none of the stars are closer to us. That means they're all the same distance away. And so that's one of the observational supports for the ancient Greek model. None of the stars exhibit parallax. Now we have to fast forward to the future, to the 1800s, and we start getting an idea, for example, that nearby stars actually do shift. We get better measurement equipment, and I think probably one of the things that really helps us out here in terms of developing technology, aside from the telescope, is the photographic plate. No longer do you have to go out, take a mental image and draw it out on a piece of paper. You can actually go out, hook a camera up to your telescope, and take an image on a photographic plate. A piece of glass with silver on it that maintains the image. Then 6 months later, you do it again. You take your photographic plates and you can compare them side by side. And you can actually flip back and forth between them to see the apparent shifting of the star. Okay? It's at that point that we're able to actually view these parallax effect. Now, you might say, why, Greg, can't we use this? Why do we need those other distance measurement techniques? And you already know the answer to that one as well. As your thumb gets further and further away from your face, you'll notice that the parallax angle gets smaller. There is some distance beyond which you will not be able to perceive that parallax angle anymore. Right? Even with the best telescopes, even with the best cameras today, that parallax angle, that parallax measurement is good out to maybe something like, we'll say 1,000 parsecs. That's 3,000 light years. Beyond 3,000 light years, the shift is just so small that we can't measure it with our technology, with our equipment. Okay? So we need better, I shouldn't say better, we need other measurement techniques to allow us to see even farther into the, first of all, the galaxy, then the universe. Okay? But the fact still remains, this is the first measurement technique that we have after Kepler's third law. And I should also mention that it's the most precise. It's the one that requires the least amount of assumptions and is the easiest to measure and therefore is the most precise. As we get further along, you'll find that we'll have to make additional assumptions for our measurement techniques, and therefore there's a degree of what scientists will refer to as error or uncertainty in the final product. Okay? Okay, so that's all I have for this video, a pretty short one. Please bring questions to class. Keep up the good work. I'll see you next time.